Hi, Finance 217. I'm about to start grading your quizzes from the other day. I'm going to put the answer key together. I figured, hey, if I'm putting the answer key together, I might as well tell you how I put it together. Again, trying to be efficient, which is why I wait until I start filming to have a beverage. Anyway, let's get started. So there are two quizzes. There was the denim chicken quiz, or just the regular chicken quiz. And there was the worm hat quiz, or just the regular hat quiz. You stare at people's feet. Sometimes, and that's weird. Sometimes you wear matching socks. Sometimes they don't. There are many kinds of footwear. Round your answers to decimal places. So basically 5 questions that we're going to answer based on this contingency table. Being that guy, I copy this stuff, drop it into Excel, which means I can now more easily answer those 5 questions which are listed here. Oh no, it's too hard to see. It's even harder to see. Not enough to see. That sounds good. So first question, what's the probability that someone wore clown shoes? Well, clown shoes are here. And it looks as though there were a total of 21 clown shoes. 21 out of the entire sample of 172 people means the probability is 0.12. Let's fix the rounding a little bit because I believe the question does say round your answers to 2 decimal places. So 2 decimal places, and let's just copy that formatting down. Then you are, after you copy, we'll paste the formatting. So now whenever I do stuff here, it will still give me that information. So if someone had sporty shoes and matching socks, 84 people had sporty shoes, 109 people had matching socks, but their intersection, the intersection of sporty shoes and matching socks, well, that's 65 people. 65 people divided by a total of 172 means about 38% of people had sporty shoes and matching socks, and is the intersection. C, what's the probability someone had matching socks or sporty shoes? All right, let's get rid of this because we don't need any fill. Someone had matching socks, so that's matching socks, or sporty shoes, or sporty shoes. Well, that appears to be 109 people having matching socks, 84 people having sporty shoes. So we just simply take the total number of people with matching socks, 109, add it together with the 84 people wearing sporty shoes, divide it by the 172 people, and we see the probability that someone has matching socks or sporty shoes is 1.12, and immediately realize that's bad news because you cannot have a probability which is over 1. The problem is you can't double count the people who are wearing both matching socks and sporty shoes. You can only count them once. Really, what we should be doing is something that is more like 12 people wearing matching socks with flippy flops, 29 people wearing matching socks with dress shoes, plus 65 wearing sporty shoes and matching socks, plus 3 people wearing clown shoes and matching socks, and then 19 people wearing sporty shoes who aren't matching their socks. And we're going to divide that sum by 172. And that gets us to approximately 74%. Put it another way, the total number of people wearing matching socks plus the total number of people wearing sporty shoes minus whatever the overlap is, because you only want to count once, divide it by the total number of people, 0.74. And that looks like the way it's supposed to look now. Number 4, of all the dressy shoes, someone had matching socks. So only look at dressy shoes, which is these 53 people, and that someone had matching socks. So we want 29 divided by 53 gets me 0.55 there. Of all the non-matching socks, which is 63 non-matching is there. Of all the non-matching socks, someone had flippy flops. That appears to be 2 flippy flops out of the 63 non-matching, which is 0.03. There's the answers to those. Part 2. The probability of making that putt for a prize during halftime of a basketball game is 0.10. 11 people putt. Although last Saturday night, it was like going through a water hazard because of the condensation and whatnot. It was a good, exciting game, though. Good guys won. Diego Friars. Effectively, what we have here is a binomial probability experiment because every person who putts that putt has a 10% chance of making that putt. And it doesn't matter if someone before you makes the putt, you still have a chance, a 10% chance of making that putt. 11 people putt. So now we're in a position where we have a binomial probability experiment where n equals 11 and pi is 0.1. Or to put it another way, to put it another way, like putting, but put. So to put it another way, we have a binomial probability experiment where n equals 11 and pi is 0.1. So this is the only column of numbers we really care about. If I happened to have my binomial probability tool handy, boom, I can say pi is 0.1 and is 11. And now Excel will do the math for me. Note that this table of numbers is the same as this table of numbers. 0.314, 0.3138 would be 0.314. Just have a little more specificity on this tool. Okay. Question 2A says, what's the probability no one makes the putt? That's x equals 0. Everyone makes the putt. X equals 11. At least one person makes the putt. It's x equals 1 or 2 or 3 or 4 or 5, all the way to 11, otherwise known as x does not equal 0. Sometimes people write that as x does not equal 0. Or if you really want to do it, x, insert a symbol, does not equal 0. Fine with me, whichever way you want to do it. That tends to be, or you could say, I suppose, x greater than 0. All of those are fine as long as x doesn't equal 0, which should be the complement of the answer we get from 2A. More than 2 people make the putt, that's x greater than 2, otherwise known as x does not equal 0 or 1. Fewer than 2 people make the putt. Well, 0 is fewer, 1 is fewer, but 2 is not fewer than 2, so we don't include 2. Notice that D and E are not complements because this, more than 2 people make the putt, 2 is not more than 2, 3 is, 4 is, 5 is, and so on, all the way up to 11. In neither D nor E do we include 2 people making the putt. And if we want things to be complements, they need to be mutually exclusive with no overlap. And these are mutually exclusive, but they need to be exhaustive as well. Collectively exhaustive, meaning that we include every possibility. And in D and E, we have failed to include 2. For 2A, no one makes the putt is about 31%, or equals 0.31. I can already tell you that this one is probably 0 because that's what's here. Again, it's not actually 0. It's possible. It's not probable, though. If we actually extend these decimal points out as far as, and so we can, all right, here we go. So that's tenths, hundredths, thousandths, 10,000ths, 100, million, 10 million, 100 million, billion, 10 billion. I believe this decimal is 1 in 100 billion. Although I might be off by an order of a 10. I got a lost count there. But we'd have to go to 1 billion Friar games or 100 billion Friar games to see 10 people, 11 people. No, because only one person putts a night. Oh, golly. We'd have to go to 1 billion to expect 11 games in a row to have somebody make that putt. You're better off winning Powerball 3 times. All right, nuts to that. 0. No, if we have 11 people shooting, 11 people don't make it. At least one person makes the putt. Well, we already said that's the complement of A, so we could say 0.69. That's at least one person makes the putt. That would also be the sum of 1, 2, 3, 4, or 5 people make the putt. We look at our status bar down here. Sum of selected cells is 0.6862, otherwise known as 0.69. More than 2 make the putt. Well, again, we can add up these. More than 2. No, don't include that one, Jeff. Do not include that one. We do not include 2 because it's either more than 2 or fewer than 2. That's about 9% if we add those up. More than 2 is 0.09. And again, it's not the complement, so we can't just throw the other one in there. Fewer than 2 would be 0 or 1. Add those 2 up and it looks like about 70%. 0.70. Cool. On to question number 3. The number of people who count their chickens before they've hatched is normally distributed around a mean of 111 with a standard deviation of 12. What is the probability more than 90 people count their chickens before they've hatched? In this circumstance, we've got a couple of things. I'm going to switch back to live camera so I can show you the picture that I draw. Ooh, and for those of you who've got the classroom chops, check this out. I got pens with colors on them, so I can do that same stuff I do in class, but on paper. So let me see if I can get started. We have a normal distribution. The 3 pieces of essential information here are that we have except the black pen doesn't work. We have a normal distribution that has a mean of 111 and a standard deviation of 12. That. So with those pieces of given information, boom. I know that I'm permitted to draw a normal distribution because the problem tells me that this is normally distributed. So I draw the normal distribution, which sort of looks like that. There's one piece of information that I can currently put on this distribution, and that is the mean. And the mean's value is 111 people who have counted their chickens before they have hatched. I know that because that's what, on average, I was told from the problem. There's another piece of information I can put on here, and that is the 50th percentile, and that's at the top. Because in a normal distribution, the mean, the median, and the mode, highest point, are all the same. In a normal distribution, all 3 metrics of central tendency are the same. And the 50th percentile is a synonym, is the same word for median. Median is 50th percentile. Standard deviation is 12. Not going to put that on there yet. What I do want to do is answer the first question, which is what is the z-score associated with 90 people? So I'm going to put a raw score of 90 people on the left side of my distribution because 90 people is fewer than 111 people. So I put it on the left. And that is a raw score in terms of the number of people. I'm also going to put a z-score on this distribution. Ooh, new pen feel. I'm going to put a z-score on this distribution. I can always put the z-score of the mean equals 0. Now, it doesn't matter if this is a uniform, a skewed, a bimodal, Poisson, you name it. The z-score for the mean is always 0. It comes from a formula. It's unique. There's only ever one z-score for each raw score. The z-score that corresponds to a raw score of 111 here, 0. Those are good pieces of information I can put on here. Now, if I spell out the process as I need to, there are 3 steps. My goal is, again, to find the z-score. So I know I have to go from a raw score to a z-score. And the tool I use to get from a raw score to a z-score is the formula. And when I'm going from left to right, I solve for z by taking x minus mu over, come on, pen, get with the program. Fresh ink. Getting the ink flowing. Z equals x minus mu over sigma. That's ugly. I don't need to spend all that time writing it in there. But I know my x value is 90. My mu value is 100. Ooh, blue writes nicely. And sigma is 12. All I've done for this part of the formula, 90 minus 11 equals 90 minus 111 over 12, is substituted into the formula the values which I initially extracted. I extracted the essential information, so I don't have to go back to the Word document of the problem. All I'm doing at this point is substituting the values that I see. And using Excel. Seen off screen, 90 minus 111 divided by 12 gets me negative 1.75. And it's negative. Z-scores have two properties. They have distance and direction. So in this case, my z-score is in the negative direction because it's less than the mean, and it has a magnitude of 1.75. With those two pieces of information, I can answer the part 1 question, which is the z-score associated with 90 people, negative 1.75. Now we got to find the probability that between 90 and 11 people count their chickens before they hatch. That's the next step. We have to take this z-score and take it to the table so that we can find an area. I don't know, I tell you, whatever they put into the blue ink is far superior to what they put in the red ink. But I need to find an area from my table. A table, it looks like this. Oh, look at that. It was some sort of neat camera trick. Here's my table. It looks a little nicer than me holding it up. And my goal is to go from the outside, which is where the z-scores live, to the inside, where the areas live. And on the outside here, I need to find a z-score of 1.75. It doesn't matter if it's positive or negative for the z-score because the normal distribution is symmetrical. I have a z-score of 1.75 that I'm going for. It's on the negative side, but it's okay because it's symmetrical. And between 111, which has a z-score of 0, and 90, again, on this side, find a z-score of 1.70, 1, 2, 3, 4, 5. See that right here? 0.05. So this would just be a z-score of 1.70. This is a 1.71, 2, 3, 4, 5. So the area that I put on my picture is 0.4599. And that is actually the answer to question B. The probability that between 90 and 111 people count their chickens before they hatch is the same thing as the area that I put on my picture, 0.4599. More than 90 people counting their chickens before they hatch. Well, that's the last step, and that's to convert areas into probabilities, proportions, percents, or percentiles. And I'm just going to use my picture for that, because the picture tells me that that big area on the right-hand side, which is half of stuff, I know it's half of stuff because the median, the 50th percentile, divides the normal distribution into 2 equal halves. And if we want to know the probability that more than 90 people, I'm going to do whatever the thing is, a chicken count. Effectively, it's all that stuff. So I just got to add up 0.4599 to 0.500, round that answer to 4 decimal places, and I believe I get 0.9599. It's a ridiculous problem, but as long as you just simply identify these pieces of information first, the shape of the distribution, what's the mean, and the standard deviation, it doesn't really matter what you're after otherwise. I'll do the second quiz because, I mean, I got to anyway, right? Tune out if you want. Stay tuned if you are. Do you? Time for Vermhat. I'm going to do the same thing, which is copy these things into Excel. Sorry. There's a bunch of people wearing hats. Some of those hats are Pat's hats. Some are not. There are many types of hats. These answers round to 2 decimal places. I'm going to copy this table. I'm going to put it into Excel on a new sheet. Control F11 gives you a new sheet. Boom. I don't like it when it does that. You know what? How about Shift F11? Control F11 gives you this macro sheet, and that's not what I want. Shift F11 is the one I want. Paste some values in there. Let's take my questions with me so I don't have to continue to Alt-Tab. Cool. Probability that someone had a beanie. I'm going to not do the double counting for C. I'm just going to answer these questions straight up so I can get to the grading. Probability somebody had a beanie. 21 divided by everybody gets me 0.17. Let's reduce the rounding. Control C, copy, shift and down arrow because I'm putting answers here. Menu key R will paste formatting. So these things all get rounded to 2 decimal places. Escape and onwards. Someone had a Pat's hat. 31 people out of 123 is going to be about 25%. And it looks good. Someone had a non-Pat's hat, which is 92, or a build cap, which is 74. But what I have to do for those two, which is, I'll just do this. Build cap and non-Pats. Can't double count 58. 74, 92, minus 58, divided by 123, about 0.88. Of all the visors, of which there are 9, someone had a Pat's hat. Equals 2 out of all the visors, 22%. Of all the Pat's hats, 31, someone had a hard hat. Pat's hat divided by hard hat. And I mean, I should raise that to the -1, but I'm not going to. Of all the Pat's hats, which is base 31 is a hard hat 2. Out of 31, 10. Here's your answers to question 1. Question 2. Assume the probability Jeff starts class on time is 90%. You come to class 9 times. Answer these things to do decimal places. Effectively, again, what we have here is n equals 9 and pi equals 0.9. N equals 9 and pi equals 9. So this is the table we need, which is n equals 9, or for the only column we need is the one for pi is 0.9, which is this one. Unfortunately, I have no horrible pun for putting things with whatever thing we're working on here. So this is the number of times over the course of a 9-day, called a 3-week span, you come to class. I'm probably going to start class on time pretty frequently. It's really what I do. If nothing else, I'm prompt. The questions we need to answer. Never starts class on time, x equals 0. Always starts class on time, x equals 9. On at least one day, x is greater than 0, or the complement of a. Yes. X greater than 0, or complement of a. More than 4 days, x greater than 4. Fewer than 4 days, x is less than 4. Note, again, these two things, D and E, are not complements because we have excluded 4. Or to put it another way, x equals 0. Will Jeff never start class on time? No, sorry. I will start class on time at least one day. Now, it has come to my attention that this particular table, now I'm not going to bother doing this addition because I use the complement rule. But if I add up 1 plus 7 plus 5, I get 13, plus 2 gets me 15. 15 plus 7 is 22, plus 7 is 9. 9 is not 0. The mutually exclusive and exhaustive part of this probability distribution says when I add up all these probabilities, they should equal 1. But if you add up all these probabilities, you get 0.999. And that is not 1, even for large values of actually, for large values of 0.9999999, you do get 1. But don't spill the beans on that. So I understand that depending on how you went about answering these questions, you might end up giving me numbers like 0.99 as opposed to 1. I'm not going to get nitty on that. However, here's our answer. 0.387 would be the answer to x equals 9. I believe it says the 2 decimal places. So 0.387 should round to 0.39. X is greater than 4. Add up those guys, and again, we get 0.999. We look at this table, and it looks like we had a bunch of zeros here, and that's 0, 1, 2, 3. There's x equals 4, and we're not including 4, so yeah, effectively, we have greater than 4 is 1. I may also accept 0.99. Here, fewer than 4, if I add up 0, 0, 0, and 0 for 0, 1, 2, 3, I do happen to get actual 0. And that's number 2. Number 3, the number of college students I know who failed to call their mom on the weekend is normally distributed around a mean of 143 with a standard deviation of 20. What's the probability that more than 118 failed to call their mom? So again, extracting essential information. First thing first, I know this is normally distributed. I know that mu is I love you, and sigma is 20. Ultimately, I'm trying to answer the question, the probability that x is more than 118, which looks like this. I didn't add this last part right down here in the previous problem, but it just keeps me from having to Alt-Tab, and I can use all my screens effectively. Those are the things I'm trying to do. Because the problem tells me that this distribution is normal, whatever we're talking about, people not calling their moms, I can draw that. I can put that on there, which is the mean of 143. I can also put a z-score on here of 0 because the z-score for the mean is always 0, no matter what the shape of the distribution. I can also put the 50th percentile on here because it's the median. Looks awfully similar to the last problem we did. Well, these two quizzes are the same, but regardless, we're always effectively following the same process. Pull out this essential information and start drawing a picture. That way our life is a lot easier. And I want to make things easier, not harder. Speaking of easier, what's the z-score associated with 118 people failing to call? Well, I just got to make sure I take the raw score, whatever I'm given there. I put on my picture 118. 118, and I need to convert that to a z-score using the z-score formula. The z-score formula, z equals x minus mu over sigma. And as is the nature of things, once you get the red pen going, it seems to want to work on its own. Let's substitute some values in here and do some calculations. $1.18 minus 143 divided by sigma, which is 20. Beep, boop, 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 boop. Let's get to 118 minus 143 divided by 20. Check the numbers. Input, negative 1.25. Again, z-scores have two parts, a distance and a direction. Negative 1.25. Distance and direction. The distance is 1.25. The direction is negative because 118 is less than. Because it's less than the mean. If I had gone, what does that appear to be? Something like 25. If I had gone 25 units above the mean, I would still have a z-score of 1.25, but it'd be in a positive direction, wouldn't be negative. So 3a, z-score is negative 1.25. I take z-scores and I convert them to areas using the table. And I need to go from the outside of the table to the inside of the table, because on the outside of the table is where the z-scores live. And then we do the magic of cameras, like chair. Oh, sorry, sound effects. There we go. All right, so there's our table. That's too close. 1.2, 0, 1, 2, 3, 4, 5. And there's my 0.05 at the top. So 1.25 gets me an area of 0.3944. And that's the area of 0.3944. That's the answer to question number 3B. Which leaves me with my picture, having already put the right half above the median on the picture, means in order to find the answer to 3C, which is the proportion of people, something, I don't know, x greater than 118. That's really all I remember at this point. I don't know the context of the question. I think people like you failed to call your mother on the weekends. There you go. Add them up. 0.5 plus 0.3944 appears to get me 0.8944, and that's the answer to 3C. Easy part's over. Hard part's doing the grading. So I'm going to go do that now.